hope this is working. All right, so we left off on Wednesday and we talked about fixed point iteration. And the idea with fixed point iteration is we want to find the roots of f of some function f of x, okay, so that is where f of x equals 0, okay? And with fixed point iteration, basically, we create a new function g of x so that g of x equals x, where f of x equals 0. Okay, so we have a few options. All right, so this is an example taken from chapter 10 in the scientific programming. So this is example. Open my pen here. From chapter 10 in basically the scientific programming with R. I don't know, scientific as using R or something. Okay. There's a textbook there. Okay, and so let's say we have f of x is the function log of x e to the negative x minus e to the negative x. Okay, so we have a few options, right? So we can say we basically just want to rewrite this so that you know, we have it in terms of x equal to something. Okay, so we want to find, well, f of x equal to 0. So we can say, all right, so we have a few options. Okay, option 1 will be to say, okay, log of x, log being natural log. So we just add e to the negative x to both sides, and then I exponentiate both sides, and I would get x is equal to e, so I'll just have e raised to the e of negative x. So I'll just, okay, so that's one option. Option 2 is we start off with log of x minus e to the negative x is equal to 0. Okay, and then so we would set this equal to g of x over here. Another one is we could just do this entire thing, x minus the left-hand side. Equals x minus 0. All right, and then we would set this equal to g of x. All right. So basically, you know, a solution to this thing equaling x would be a solution to the original thing being equal to 0, right? Same thing right here. If we find where this thing is equal to x, that would also tell us where the original f of x is equal to 0, right? Option 3 is we could add x to both sides, and we can have x plus log of x minus e to the negative x is equal to x. Okay. Either of these things. Okay. These are all different options that we could use for what g of x could be. So basically we just rewrite the function f of x. F of x equal to 0, or we move some terms around so that we have x equal to something, and then now that's going to be equal to our g of x. This is week 7. Monday. Okay. All right. So far, so good? Yes?
Is there one option that's better than the other?
No. It's a lot of times like, so you can't tell. You look at this and you're like, I guess which one should I use? And then you use some, and it turns out option 2 happens to work the best, and option 3 doesn't work at all. Option 1 also works, but yeah, there's no. Kind of the whole point of numeric methods was to avoid having to do math, and if you want to find out which option is going to work the best, you got to do some math. Okay, so basically, fixed point iteration will work when there's like a delay in my pen. When the slope at x is less than or equal to 1. I don't know what symbol that is. Less than 1, actually. So the absolute value of the slope has to be less than 1. Okay. All right, and then so what does this look like when we diagram this out? So let's say we've got so here this is the line y equals x, or this will be g of x, not g of x. Yeah, this will just be y equals x, right? And then let's say we have some function, and that's terrible. Oh, man. Okay. All right. So there we go. All right. So the solution is going to be right here, right? This is what we want to start. This is what we want to find. Okay. And so basically you just start at some location, x at time 1, okay, and then you find, okay, well, what is, I'm sorry, this is the entire algorithm for fixed point iteration, is that x at time n plus 1 is equal to g of x at time n. Okay, so if we start at x1, this location right here is g of x at time 1. Okay, and basically we say, all right, what is, all we're going to do is we're going to just plug in g of x at time 1, x2 is equal to g of time x at x1. That's all it is. Okay, and we can kind of illustrate this. Here we can say, if I go over to where what g of g at time x equal to 1 is, at x1 is, this is the location right here where this is my x2 right there. Okay, so that's x2, and then now that I've plugged that in, this gives me a g at time x3, g at time x2, and cutting over to over here, right there, and finding out, okay, this takes me down to here. This is going to be x at time 3. X at time 3 is equal to g of x at time 2. And we can see that continuing this out will eventually lead to convergence right there, where g of x is equal to x. Okay. So the code here is very, very easy to write. Basically, you just run some kind of loop. So here's some pseudocode. All right. So we'll call this. So we can write a function, and so we'll call this, fixed point. Will be a function of. It needs to be a function of basically g of x, and then we'll give it some options, such as the starting point. So we'll have a x0. That's kind of our starting point. And then we'll probably have a tolerance term that says this is the point where we've converged, right? Because we don't want to run forever, because technically we could run forever. It's just at some point we've got to say, all right, at a certain point we're going to stop. So we'll have a tolerance, I don't know, with a default value of 1 times e to the negative, I don't know, -6 or something. Okay, that's arbitrary. All right, and then and in here we would need the function g, and so we would basically just say so we'd start off where we'll set x0 to be our x old term, okay, and then we'll have x new will be the function g at x0, okay, and basically we'll run a while loop, and the while will be as long as x old minus x new, and we'll do the absolute value of this is greater than the tolerance. All right. So as long as this is greater than the tolerance, we'll keep going. And inside the while loop, all we do is we just x new, our current new, will become the old, and then we will reassign new to be g at x old. And that's it. Yes? So basically, mathematically, we want to find where the thing actually equals g of x is equal to x, right? And based on this, if I zoomed in here, okay, if I zoomed in right here, we would just have you would have this line and this line, and then it would just, you'd have an even tighter little basically this kind of action, right? And then we could further zoom in here, and then it would just continue on ad infinity, right? So to prevent us from running forever, we're going to just say, you know what? If the next iteration is less than 0.0001 away from my current iteration, we're going to say it's converged. Okay? Otherwise, we can keep going, and then we'll eventually run into a problem where we have a machine error, meaning that our floating point numbers can't represent the differences between the two things. But basically, we just giving it some kind of tolerance number, we just say keep going until you get within 1 millionth of the thing, and we'll say that's good enough. We'll say that the answer hasn't changed. We're good enough. Question?
So I think it's really important to decide a starting point, because if the starting point is too far, there will be like a ton of
that's true.
implications.
Yes.
So how do we decide a really effective starting point?
Yeah, that's you don't really know. Okay. Basically, like if you have the ability to graph it, and then eyeball it and say, oh, well, this looks pretty close, and start there. Okay. That's. But if you don't have the ability to graph, then you can't tell. You just You start it, and then if it converges, then great, and you can just try to test it out.
So the computer just randomly chooses a point?
No, you don't want to have the computer randomly choose a point, because random would be what, truly from negative infinity to positive infinity, and we can't do that. But yeah, if you have the ability to graph, then start there. And if you don't have the ability to graph, then you'll have to make some guesses. But yeah, the starting point is important, and if you have a terrible starting point, it will take a while to converge. That is true. Okay, does this kind of make sense as far as the pseudocode goes? Yes.
Why does it only work when the slope is less than the absolute point?
Because if it's the other way, then it starts diverging in the opposite direction. So if I have this, and then and the actual point is let's see, it goes like this, okay, and so here, if I plug in this value, if this is my x at time 1, and I say, okay, let's do g of x at time 1, okay, that's going to be right here, and that would take me over to here, okay, and then when I say, all right, well, this will be x at time 2, and I go up, and I say, okay, well, what is g at time x2? It goes over here, and then you can kind of see that it's going to diverge. Okay, so if we have the slope going the wrong way, then that could be a problem. Now, you might be able to fix this by just rewriting the equation in a different way. You do x minus the f of x or something instead of doing x plus f of x or something. So, okay, I'll just. Am I able to undo all of this? Okay, just so this doesn't show up in your notes. Yes?
So the function is returning x, like once we exit.
Oh yeah, we should, at the end of the while loop, we should have the function return x new. Yeah, okay. Something like that. Okay, so that's fixed point iteration. Is that okay? All right. Let's try another numeric method. This one you might have learned in calculus, Newton-Raphson method. So another. You didn't?
What is it?
Newton's method, Newton-Raphson method. You should have learned this in calculus. All right, whatever. Okay, you didn't learn it. Well, I will teach you now. Okay. Another root finding method. Okay, this is called Newton-Raphson method. Okay, so this is how it works. This is you've got some function f of x, and we want to find where find the roots, right? Find where f of x equals 0. Okay, so find solutions to this. Okay. All right, so let's say this is our function, right? So the root is going to be right here. This is what we want. Okay, we want to find this. We want this location. All right, so let's say we start somewhere, okay? Let's say this is going to be our x0. What we do this time is we go up and we say, okay, well here is f of x0. F of x0 is right here. And then what we do is we draw a tangent line What does a tangent line look like here? So I draw a tangent line to the curve at f of x0. F, right? And where the tangent line crosses this spot right here, all right, so 1 is start at x0. 2 will be find f of x0. All right, I mean, this is not really it, but okay. And then draw a tangent line at f of x0, and where the tangent line crosses y equal to 0 will be x1. So this will be our next location. X at time 1 is this spot right here. Okay, and then once you've successfully done that, then you just repeat. So this is going to be x at time 1. You go up to the curve, and you have f at x at time 1, and then you draw a tangent line. And that will be like right there or something, okay? And ta-da, this is now x2, and so on and so forth, okay? And eventually, you know, if you zoom in, this will get you very close to, it will get you to where it converges there, okay? All right, so what is the location of x1, right? How do we find this tangent line, and how do we get this spot right here? All right. So, okay. Well, we have to do a little bit of algebra. All right. Okay. So, so here we're gonna just kind of take a look at this triangle. Okay. What is the height here? The height is equal to f of x0, right? Okay. And okay, so this, I'm going to just label this the rise, okay, and then this will be the run, okay? So what is the relationship between the rise, the run, and the slope?
Rise over run.
Okay, so we have slope, exactly, right? We remember this from algebra, right? You didn't learn this in calculus, but I hope you remember this from algebra. Okay, so slope is rise over run, okay? So what is going to be the length of the run? All right, okay. All right, you guys are getting ahead of me, all right? The run is the rise divided by the slope, okay? Okay, is that all right? Yes, so far so good. Okay, and we said the rise is equal to f of x0, right? Okay, and what is the slope? This is where we take the derivative of f at x0. All right, is this okay? All right, and then so what we have is x1 is going to be equal to x0 minus the run, and we have x1 equal to x0 minus f of x0 divided by f prime of x0. Yeah. Okay, and then we just generalize this because we're going to just repeat this at all times. So we just say x at n plus 1 at time n plus 1 is equal to x at time n minus f of x at time n divided by f prime at time xn. Okay, and that is the Newton-Raphson method. Okay, that's the entire thing. Ta-da! All right. Okay. Should we write some pseudocode for this, or can we do this on our own? No, you guys are too scared to do this. Okay. Okay. All right. So, Newton-Raphson method basically says this is going to be your next iteration is xn minus f at the function, the rise divided by the slope. All right. So if, this thing shows up in the book just like this, but if you forget, it's easy to derive it also, right? You just say, okay, I just have to draw the triangle. I know the rise, I need to figure out the run. Huh? Yeah, so, okay. So this is the tricky part is the derivative. We have to encode that into our function, right? So basically, we need to first create a function. We need a function f. All right. So let's say we're going with let's say f of x is going to be x squared minus 4 or something like this. Okay. So we need a function of f that will returns both f of x and f prime of x. Okay, so I'm going to just write f is a function of x, all right? And then what we will have is we'll have fx will be x squared minus 4. And then we'll have f prime will be 2x. And then what we will return is we will combine fx and f prime. There you go. Okay, and then therefore, if we plug in what is f at 5, this will give us the answer here will be what is this? 25, 21, and then and 10, right? And then so if we want the thing, we would have f of 5 at 1 will be 21, and then f of 5 square bracket 2 will be 10. Yeah? I don't know. I don't know off the top of my head, so. Yeah, so the hard part is maybe you have to find the derivative, right? That's why we have Wolfram Alpha to find derivatives for us. Or in the worst case scenario, we can approximate derivatives, right? If let's say like we couldn't figure out the derivative, is there another way we could do the derivative? It's like an estimated, like if we needed to estimate f prime, estimated f prime, this would be what? Like if we couldn't figure this out, all we would do is we would just do we would have to figure out f of x minus, or it's actually f of x plus some tiny delta, right? Minus f of x divided by the delta, right? And if you say delta is like 10 to the minus 5 or something, this will give you a pretty good approximation to what f prime is. So you would just code this up also. It's not that big deal. Okay. Okay, so anyway, we have this. So we have our function f, and then, all right, let's do our Newton-Raphson. Newton R will be a function. So it's a function of, we need our f, and then we need an x0, and then we would have a tolerance as well. And then all we do is exactly what we said we were going to do. So we have x old will be x0, and then x new will be x old minus f of x old, the first value, divided by f of x old. Something happened. Seems successful, thank you. Where are we? We're week 7. I don't know where we are. Oh, here we are. Monday, okay. Here we are, okay. F of x old and the second value, right? And then, yeah, I guess this is the first iteration, and then you basically just throw exactly while x absolute value of x old minus x new is greater than some tolerance. What do? We're going to just do this thing. X new is, oh, I guess this I should throw in here. Okay, well, anyway. Yeah, so it'll be x old minus f of x old. I might have to, you might have to clean up this code a little bit. But this is, this is pseudocode anyway, right? Okay, and then, yeah, I would have to, figure this out, whether it belongs on the, whether I need it on the outside of the loop or not. Okay, so anyway, you have this, and then at the end of it, you return your x new value. And that's it. Okay. Is that okay? So that's Newton-Raphson method. And again, if you can't figure out the derivative directly, analytically, you can always estimate the derivative using kind of a numeric method, which is you just take the function and then you add what we call a perturbation. Okay, you just add just a tiny delta along on the order of 10 to the minus 6, 10 to the minus something. Okay, just a tiny little thing. You see what's the difference it caused there, divided by how big your delta was in the first place, and that will give you an estimated f prime, and that will work pretty much just as good as this. Okay. All right. Any questions on this? These are all we're just covering a whole bunch of root finding methods, right? We want to find functions where the function crosses 0. Okay, another one. We've got the secant method. All right, so what's a secant line? Yeah, we just draw some line, right? Connect 2 points. Yeah, okay. So you got some curve. This is like the hardest part, is drawing the curve. I gotta draw like better. Oh my gosh, my curves. Like you want something with at least a little bit of curvature in it. Okay. All right, so we'll start with this curve. Okay. And then so secant method, it's similar to Newton-Raphson, except it's not, in that you need 2 starting points, okay? Huh? Yeah, 2 starting points. Okay, so you'll have basically, I guess, an x0 and an x1, All right, so let's say we have x0 here and x1 here. And then you go up and you say, okay, this is f of x0. And you go up to here and you say, okay, this is f x1. And then you draw a secant line that connects these two things. All right, and there you go. All right, and then guess what? This spot right here is going to be x2, okay? And then you come up and you say, okay, here is f of x2, and then you draw a secant line between this one and this one, okay? And this gives you x3. Okay, all right, so how do we do this? Okay, so let's take a look at this triangle. Okay, so we're going to take a look. So we'll start at x1, and we're going to try to figure out how do we get to x2, right? So we've got we got to figure out. So here's my rise, and then we want to figure out the run, right? Okay, so what's the rise? The rise is going to be f of x1. Okay, and then what's the so what we have is run is equal to slope divided by rise. What was it? Rise divided by slope. Okay, all right. Yeah. Okay. So the rise is this. Okay, and what's my slope? Huh? Okay, so yeah, so the slope is determined by these 2 points, right? So we have to kind of look at, I guess at, I don't know, this triangle here to get, this is what determines my slope. So here I have now a rise and a run here. Okay, so the slope is going to be the difference between f of x0 minus f of x1, and the run is going to be x0 minus x1. Right? So that's the slope, and this is my rise. So what is x2? x2 is going to be equal to x1 minus the rise, f of x1, divided by the slope. So I would multiply this by x0 minus x1. I'm just going to invert the slope, flip it around. F of x0 minus f of x1. Okay. The book has the same thing, except they have x1 minus x0 and f of x1 minus f of x0. So sorry, they have these terms flipped around, but it's the exact same thing, right? Okay. So so sorry, I deviated from the book just a tiny bit. Okay, so then in general form, we have x at time n plus 1 will be equal to x at time n minus f at x at time n times, and then now I'll copy the book notation here, but they have xn minus xn minus 1 divided by f of xn minus f of xn minus 1. I don't know. It's because I messed up. But it's the same. It's the same, right? If you got 1 minus 2 divided by 3 minus 4, that's the same as 2 minus 1 divided by 4 minus 3. So, or did they just end up being the negative? No. Did I mess something up? I probably messed something up. Okay. Rise divided by run. Okay. I might have to double check something. I think it's the same. It's the same because I think you're just going to have the negative on the top and negative on the bottom, so that's the same. Okay, and that's the secant method. All right. There's no point in writing the pseudocode. It's going to look exactly the same as what you did before. You don't need to have a derivative anymore. You now have the secants. Okay. All right, and then the last one. I know we're covering all these methods. Bisection method. Oh, is this okay before I move on? How we got the next location, x2 and x3 and all of that? Okay, bisection method. This one's really like, I'm too, I don't even want to think about, this one's really throwing the computer at the function and saying, do your best. So the other ones all might fail. Like they work a lot of the times, but they could also fail. Bisection method, guaranteed to work. As long as it's continuous. Okay? As long as you have a continuous function and not something that's like gonna jump across 0, bisection method will work. Okay? So this one is guaranteed to work as long as it's continuous, okay? Okay, and basically you you start with, you have an x0 and an x1, and f of x1 has to have the opposite sign f of x0. Okay, that's, so you just start, one is above and one's below. Okay, and then you say, all right, let's find a spot halfway between x1 and x0. Okay, so that's like right here. Okay, so here you have x2, right? x2 is going to be equal to x0 plus x1 divided by 2, right? And then you evaluate, right? Evaluate f of x2, right? And then you say, okay, what is the sign of f of x2? Okay? And then based on the sign of f of x2, you throw away the one that has the same sign, and you keep the one that has the opposite sign. Okay? So throw away x1 or x0. Okay, the one where, what is that? The one where the, you know, f of x1 or x0 has the same sign. Okay, and then so you basically, you have this, and then you just continue, and you say, okay, I've got x0 and I've got x2. All right, the next point I'm going to have, x3, is going to be halfway between there and there, and then you just continue to just cut it in half, and you throw away the point that has the same sign. So here we would get f of x3 right here, and so we would throw away this one. Okay, and you just keep cutting your window in half. Okay, and that's the bisection method. It's going to be guaranteed to work. It probably also takes the most number of computations, okay, as compared to the other methods, but it works, and it's also very, I think it's very easy to visualize how this one works. Right? There's no slopes, no angles. Just do we have, is one above 0 and one's below 0? Great. Let's cut it in half, and then just make sure that your endpoints, one is always above 0 and one's always below 0. That's basically it. Just continue it until you reach some until the difference between xn and xn plus 1 is below some tolerance, and then your best guess will be the mean between those 2 points, right? You're just whatever your stopping criterion. So you say x1 and xn, and the next iteration is the difference between those is less than 1 millionth. You say, okay, great, that's going to be my best guess. Okay, that's that for root finding. Okay.